Right, so this is the last lesson from chapter 7. Looking partially at a few ways we can solve an exponential equation algebraically without using a logarithm. We only have a few options, as well as about more with modeling exponential equations and then solving them graphically, which requires a graphing device. So first, this equation here can be solved algebraically without using logarithms, and that's because there's a way to make these two bases the same. And by that, right now, I have a base of 8 and I have a base of 16. They're not the same, but I can make them the same by writing them, in this case, both as powers of 2. For example, 8 to the power of 3x minus 2 is the same as if I write that 8 as 2 to the power of 3 to 3x minus 2. Because 8 is the same as 2 to the power of 3, and 16 is the same as 2 to the power of 4. And so now notice they both have, I have expressions that are a bit messy, but I can clean them up. Both have a base of 2. And so now if I just remember my exponent laws, I have one power raised to another, I can multiply those. So this expression on the left becomes 2 to the power of 9x minus 6. On the right becomes 2 to the power of 4x plus 4. And now I have the exact same base for each. So the only way, if I want to solve this equation, that I can make this side of the equation equal to this side of the equation is if just the exponents equal one another, because I've already made the bases equal to one another. So at this point, I can just focus on making 9x minus 6 equal to 4x plus 4. Which, a couple quick steps, you get to x equals 2. Right? Subtract 4x from both sides. Add 6 to both sides, something like that. Lots of options to get to there. Okay, and so let me give one more example. A little bit messier, but same idea. So there's a way to make these bases the same. And at some point we need to realize that 27 and 81 are both powers of 3, even though 81 is in the denominator. That's it. 27, again, the same as 3 to the power of 3. So that's all to the power of x minus 2. On the right-hand side, 81 is 3 to the power of 4, the power of x plus 3. All right, so what I can do now, though, is first on the left side, I have one power raised to another. I can write this as 3 to the power of 3x minus 6. On the right-hand side, I'll write it as 3 to the power of 4x plus 12. But I still have 3 in the denominator, but again, if we think back to what negative exponents mean, which means division, which is what a denominator is, denominator, you're dividing by something, I can write this without a fraction. And so if I look at what I have on the right side, 1 over 3 to the power of 4x plus 12 is the same as just 3 to the power of negative 4x plus 12. And now, if I look at what I have right here and right here, if I can just make those the same, I have solved for x. Now I'll distribute the negative. Again, in this case, I have to remember what negative exponents mean, which is really division. And then now I'm just solving a fairly basic polynomial equation. Got to be careful with my negatives, but in the end, I should get x equals negative 6/7. Again, the 2 steps to get from there to there, I don't really need to show you. All right, I will say though, if we can't find a way to make our bases the same, then we need to either solve it graphically, which is what I'm going to do going forwards, or use logarithms, which are the next lessons. Okay, so next let's talk about compound interest. And I have a series of very similar questions here that get progressively towards more and more general. So for all of these though, we have an investment, and the initial investment I'm calling A naught, the initial amount, the amount at time 0, and we call that, that little subset 0, we call that naught, but it's actually spelt like this. Oh, the English language is so silly, but it's just another word for 0. So the amount at time 0. But I'm saying all of these have a 5% interest per annum, which means per year. But it doesn't necessarily mean you get the 5% all at once. So every year there's a total of 5% kind of added, but the number of times it added could be all added all at once at the end of the year. It could be added in little chunks throughout the year. That's what we call compounding, how many times you compound it. And so in the first scenario, we want to look at the value after 10 years if the initial amount is 50,000 and it's compounded monthly. That's the real thing I care about here. Okay, that's it. What is this going to be worth? And I just want an expression. So the amount of money after 10 years is going to be the same as the initial amount, $10,000. Oh, sorry, $50,000. Helps if I read my own question. Times, now let's say it was compounding once a year. It'd be times 1.05. Because every time you multiply a number by 1.05, that's the same as adding 5%. And the reason it is, it's because adding 5% to something is the same as keeping everything you had at first plus an extra 5%, which is 105%, which when you decimalize it is 1.05. And really, you can think of it as 1 plus 0.05. All of the amount you had at first plus the extra 5%. And when you multiply by that, you add 5%, and that's why that's 1.05. If it was compounding once a year, if every year you added 5%, it would have something like this. But if you're compounding monthly, every month you don't get 5%. Every month you get 1/12 of 5%. And so the way I can show that is to just go 1 plus 5% divided by 12. And I'm not even going to bother decimalizing. I'm going to leave it like that. It's just 1 plus 0.05 divided by 12. That is how much money is being added every month, 1/12 of 5%. And it's happening repeated times in 10 years. So in 10 years, how many times are you going to get this little bit of monthly interest added? Well, 10 times 12 months, so 10 times 12. And notice, if we're thinking in years, it's 10 times the number of compounding periods. And that 12, which because it's monthly, we see twice in the equation. It's dividing the interest, because every month in this case, you get 1/12 of 5%, but it's happening 12 times a year. Now, I'm not going to bother calculating this. The question does ask just for an expression. I have an expression. Let me now look if I adjust this. For the next one, the only difference is it's t years instead of 10 years. Well, I'm sure you can see then the only difference in the equation is going to be a t instead of the 10. So A equals 50,000, 1 plus to the power of 12t. And so yeah, I can change t to any number I want, and this will be the same. Okay, so the number of years is not an issue. So now what I'm going to do is focus on just 1 year, but if it's compounded daily, what difference does that make? Still the same initial amount of 50,000. So same initial amount, the amount of money after 1 year is going to be 50,000 times 1 plus, but now it's compounded daily, which means every day you don't get 5%, you get 1/365th of 5%, assuming it's not a leap year. So divided by 365. And in 1 year, this happens not once, this happens 365 times. And I could put times 1, because it's 1 year, but obviously I don't really need that. And so again, if I compare this to the last few, notice the only difference really is what I have inside the base of my exponential expression. Last time was 1 plus 0.05 divided by 12. Now it's 1 plus 0.05 divided by 365, because that's the number of compounding periods, because that's the number of days in a year. All right, so what if now I just change it from 1 year to 10 years? Well, all I'm going to do is take the exact same expression above and change that 1 to a 10. And more, I'm hoping you can see that I can change any of these numbers, and I'll get a similar expression. So 10 times 365, the time times the compounding periods. And so for the last one, it's the only thing that's not a variable is the interest. It's still 5% per annum, but everything else is a variable. The initial amount I don't say, the time is just t years, the compounding periods is n times a year. N can be whatever number we want. And so in this case, the amount of money is going to equal my initial amount. Before it was 50,000, now it's just a naught, I don't say, times 1 plus, we know it's 5%, divided by the number of compounding periods, in this case just n. And that's going to be to the power of the time times n. And so this is pretty much as general as you can get. The only difference is, all of these have 5% in common. So if it was 6%, that'd be 0.06, and so on. I mean, that can be really any number. So we can see in general, we could have this. Although I'm always reluctant to write down generalize formulas too much, because then I feel like people just start memorizing formulas, which we don't really need in here. But this is the general compound interest formula, if you wanted one, where R is the rate of growth per year as a decimal, and everything else I've already explained. All right, but again, what's more important than that formula, because I'm going to erase that, is understanding how I got to this. And really, in a course like this, we should just understand why this works and be able to come up with it on our own to try to memorize a formula, because this is not a compound interest class. And while it'll come up at times, it's not, there's a lot of other things I want us to understand. So hopefully it just makes sense, step by step, how I got to this. That said, let's look at something that does not have to do with compound interest. And the population of bacteria, grows exponentially, at least at first. And I just give us, what I say here is the population of bacteria doubles every 6 hours. So how many hours will it take for the population to increase 2,000 times? So first, let's think about what it means. Well, it doubles every 6 hours. So I'm going to use A for the amount of bacteria. So I need to know the initial amount. Well, they don't tell us the initial amount, so let's just go with A naught. And then we don't tell the initial amount because it doesn't actually matter. What matters is that it doubles. So my initial amount will be multiplied by 2 every 6 hours. So how do I show that as an expression in terms of time? Well, if I just put a t right here, that would be correct if every single hour my initial amount doubled, right? Whatever this initial amount was. If it's just to the power of t, 2 to the power of t, that means, assuming t is in hours, then when t is 3, it's going to be the initial amount times 2 to the power of 3. It'll double literally every hour. I want it to double every 6 hours. So I want to slow this down. So I don't want this to be t. I want this to be t over 6. And we saw similar things in the first lesson from this chapter. And notice when t equals 6, we know it's going to double once because it takes 6 hours to double once. And notice 6 divided by 6 is 1. And so you have an exponent of 1 right here. And so your initial amount we multiply by 2 once in 6 hours, which is exactly what we know should happen. And so if it doubled every 10 hours, it'd be t over 10. If it doubled every 2 hours, it'd be t over 2. And if it doubled every hour, it would just be to the power of t. That said, how long does it take to increase by 2,000 times? Well, that means my final amount will be the same as my initial amount, but times 2,000. So I'm going to erase the left side of my equation and change it to 2,000 times A naught. Right, that's what that really means. My initial amount is increased 2,000 times, so 2,000 times A naught. At this point, I can just divide both sides by A naught and just focus on this. 2,000 equals 2 to the power of t over 6. So the initial amount doesn't actually matter. Now with that said, if there's a way to make 2,000 written as a power with a base of 2, then I can solve this algebraically, but there's no convenient way of doing that. So either now I need to solve this, I need to either solve using logarithms, which again we're not going to get into yet, but soon, or solve by graphing, which again is an important part of this course. And so to solve this by graphing, the most general way for any equation is to graph the left and the right side separately and see where they intersect. And that's what I'm going to do right here. So I'm on the Desmos, graph the left side, y equals 2,000, the right side, y equals 2 to the power of, I'll put x over 6. Okay, if I look at my graph, I want to compress my scales. So I'm trying to see where my y is at 2,000. There it is. And it'll take about 65.79 what? Well, the units, I know by looking back at my equation, I know my units were in hours because I made up the equation myself, right? I know that t stands for hours, so I know my answer is about 66 hours. I noticed solving it graphically was really quick, and it applies, again, repeatedly throughout this course. I never want us to lose sight of that. All right, so let's look at the last question. So looking at, again, some data, this time comparing the cities of Surrey to Vancouver based on the 2016 census information. So in the year 2016, and every 5 years, there's a census that is released with a really detailed, in this case, also population information. So in the year 2016, Surrey had a population of about 520,000. And in that time, it grew by 10.4% over the previous 5 years. Again, every 5 years, only every 5 years we get really reliable data on the populations across the country. And so in the year 2016, we knew Surrey had about 520,000. I just rounded it. And it grew by 10.4% over 5 years, not in 1 year. compared to that to Vancouver. City of Vancouver is larger, but it's growing more slowly. And so at some point, that means Surrey must overtake Vancouver if they continue to grow at this rate. And that's what the question is asking. In what year will Surrey overtake Vancouver if they continue to grow at this rate? All right, and so that said, I need to come up with expressions for the population of Surrey over time and Vancouver kind of separately. So let me focus on Surrey first. And so for Surrey, we know the current amount, or 2016 amount, was 520,000 people. I'm going to put 520. Okay, that's this. You can think of that as the initial amount, assuming we're starting in the year 2016. Times, it grew by 10.4%. Well, adding 10.4% is the same as multiplying by 1.104. That's it. To the power of what? Well, we're trying to figure out the time, but we don't want to put a t right here because that implies most likely that every year Surrey grows by 10.4%. It's every 5 years. So I need to slow this down. And we saw that in the last sort of question, if I divide by 5, that's how we kind of essentially slow this down. So every 5 years it grows by 10.4%. And that expression there, that's all highlighted in yellow, models the population of Surrey in thousands, because I just put 520 instead of 520,000, in years since 2016. And then for Vancouver, it's going to be very similar, except it'll be 630 times 1 plus, or I'll just put 1.046, because it grows by 4.6%, but not every year, every 5 years. So notice the work we did with compound interest doesn't really help us here, because compound interest is a very specific calculation. This is different. Just all we were told is that in 5 years, Surrey grew 10.4%. Vancouver grew 4.6%. Populations aren't compounded like money, because money is actually like literally a calculation that a bank performs. This is, people moving, people leaving, people dying, people being born. It's just, I don't have as much data, and all I know is this. Like I said, grew 5 years, 10.4%, or 4.6%. But now, to solve this, algebraically would be a pain. Even if you know how to use logarithms, this would be a pain. To solve this graphically is quite pleasant. I'll say solve by graphing. So, how do we solve by graphing again? Hopefully it's kind of becoming more and more intuitive. Graph it as a system. Graph the left side of the equation, graph the right side, see where they intersect. And so, let's see. I'll kind of go back to my basic zoom settings. So the left side, I'll put y equals 520. The 1.104 to the power of x over 5. And if I just zoom out for a moment, and I'll compress my y scale down, so this is modeling how the population of Surrey is changing over the next 40 years. Right? So just this kind of shows me how Surrey is kind of changing. You can see the populations from 2016. All right, so now if I graph Vancouver, this was 630, but growing at a slower amount. There's the population of Vancouver, modeled how it's changing, and here's where they intersect. So about 17.7 years from 2016, not from now. Right? And I know it's from 2016 because if you look at both my equations, the initial amount is 520 or 630, which is the data for 2016. And so in about 17.8 years, roughly 18 years from 2016, according to our model, Surrey will overtake Vancouver. And so if I go back here, when solving by graphing, we get t is approximately 17.8 years. But again, we can't forget from 2016. And so that means in about the year 2034, roughly, according to this, according to the data, and assuming that the cities grow at the same rate. And the farther we get into the future, the worse that assumption is. But just from a quick calculation, looks like Surrey will become the largest city in the province in about the year 2034. All right, and so to go, at this point, besides working with some problems like this, most of this lesson is really about coming up with exponential models for things and perhaps being able to solve it graphically or solving it algebraically. But going forwards, now we need to learn about logarithms so that we can solve everything algebraically. Right? So with that said, I'm